All right, here we go. So power series. Okay, so the first thing we want to note here is when we started doing series, all the ones we looked at started with n equals 1 because, as we said, that related to sequences really well. When we do sequences, we liked having A1 be the first term, then A2, because then that number, that subscript, is the number which term in the list it is, right? By starting with number 1, so for sequences, we like this because then we knew A4 was the fourth in the sequence. It was the fourth term of the sequence. And A100 will be the 100th term in the sequence. And so we started off writing series that way, right? Adding all these up, we started off with n equals 1. But then we're starting to see some, it's very common that you'll start with 0. Now that we're working lots with these series, it's often that you'll see them start with n equals 0, and that doesn't faze us. We just know that the first thing that we'll add to the sum will be when 0 is plugged in rather than when 1 is plugged in. That's not too hard. So with the power series, we know this is our geometric series. We can rewrite it starting from n equals 0. And so in order to do that, let's write out the terms first the way we know it. So using n equals 1 to infinity. You see this and you think, what? You see this and you think, what? What is that mathematically representing, that notation right there? So, Ashley, who's Ashley?
So A plus A times R
Uh-huh.
plus A squared.
Right. Okay. So it's A plus AR plus AR squared plus AR cubed, right? And so if we wanted to write it starting with n equals 0, we need to get the exact same terms. So it's the same sum, right? So we just need to now and this should be really easy, we just need to revise what this is so that when we start at n equals 0, we get the same exact terms so that it's the same exact sum. So what will the formula be? So that starting with n equals 0, we get these exact same terms. Should be really easy. Go ahead.
AR to the n.
Yeah, so this should be AR to the n. Right? AR to the n is going to generate those exact same terms if you start with n equals 0 rather than n equals 1. So you often see the geometric series written this way. Instead of relating it back to sequences where we start with the first one, n equals 1, then n equals 2, we'll just start with n equals 0 and do AR to the n. A little bit cleaner, okay? And R is the same, so it's the same requirement for convergence that R is between -1 and 1. Okay, make sense? And so this is an example of what's called shifting the index. Shifting the index. And notice what happened. When we shifted the n value where we start, we shifted it back 1. What happened to the n in the formula? We ended up adding 1, right? So if you're going to start back at an earlier n value, then you need to bump up your n values in the formula. So that you end up getting the exact same terms. Does it make sense? Yeah. So that's an example of shifting the index. And you're going to have to do this for some of these problems. Shifting the index. Question?
So if you shift the index and you start at n equals 0,
Mm-hmm.
you still call the first term the first when you plug in 1? Or
Yeah, so the first term is now when n equals 0. Yeah, the first term is now when n equals 0. So it doesn't have that kind of convenience anymore, but we're okay with it because we can just go with it, right? We know that the first term you're going to get is when you plug in n equals 0. That doesn't faze us. Okay, so what is a power series? A power series is a series of this form. We've got something new. What's our new friend here? involved in a power series? What is here that we haven't seen before? X. Okay, so X. X is a variable, like it is a variable in functions, right? X is a variable like it is in functions. So a power series is when you have some coefficient, and we call it the coefficient. The nth coefficient is the coefficient of when you have x to the nth power. Okay, so write out what this means, right? So write out, you see this, you think what? You see this, you think what? Write out what that is representing. Sarah, did you get that? Okay. What would the first term be? C0. Any more? So it'd be C0x to the 0, which would give what? Well, x to the 0 would be 1, right? So our first term is C sub 0. C sub 0. Second term is C sub 1 x, then C sub 2 x squared, etc. Okay, what does this kind of look like? What does that look like?
Geometric.
What's that? Yeah, this is like a polynomial, right? So this is like a polynomial. So a power series is something like an infinite polynomial. Okay, now notice the coefficients are changing with n. Coefficients are changing according to n. And then we can think of x as an input variable, and that's what makes this kind of like a polynomial with an unlimited number of terms. So you can think of this kind of like a polynomial function. But you just keep adding terms, right, with higher and higher powers of x. So far we've just seen series as representing potentially just a number, right? When you add up all the terms, you potentially can get a number, or it would diverge. Well, now we see a power series being used to create something of an infinite polynomial, like a function. Okay, so then this begs the question, right? So for what values of x will the series converge, and for what values of x will it diverge? So not only is each term a function of n, but also x is involved. So x is going to play a big role in the convergence of this. Okay, questions on what a power series is? Okay, so there's our basic form. We already wrote that. So here's an example. X to the n over 2n minus 1. So in order to find for what values the series converges, we're going to use the ratio test. And just keep x as it is. We're going to keep x as it is through the whole process. And then once we get to the limit, then we can evaluate the limit and analyze what's going on with x. So why don't you practice this? So you set up the ratio test. And do the math, okay? So set up the ratio test and simplify the result until you're ready to evaluate the limit. And you're just going to hold on to x the whole time. Hold on to x. You don't have to whisper. Brady, how'd you do?
I got.
So tell not the answer. What did you start?
I did x to the n plus 1
Okay.
over 2n plus 1.
Uh-huh.
Multiply that, and it's all absolute value, times 2n minus 1 over x to the n.
Almost. So what was the denominator of when you n? The first x to the n plus 1 over what?
The denominator of the first term, 2x to 2n plus 1, because you have to change it to 2n plus 2.
Oh, you just simplified it all. Okay, I see.
Yeah. Oh, yeah, sorry.
I was hearing 2 times n plus 1, and then you were done.
Oh, yeah. Sorry.
All right, yeah. So this should have been your first step. Okay, and then how'd you go from there?
And then I switched the denominators.
Okay.
Just the way you group them.
Yep.
And then, so the x to the n plus 1 over x to the n, you just get x on top.
Mhm.
There's just one more x on the top.
Mm-hmm.
That one's just x times, and then it's 2n minus 1 over 2n plus 1.
Mhm.
I just got 1 for that,
Mhm.
so I just got x. Because it's x times 1.
Okay.
Or yeah, absolute value x.
And this is after you take, so when you take the limit, so as n does things, x doesn't care what n does. So our limit just is x, right? This is the limit. And so what did we say? When does it converge according to the ratio test? Well, no, what just in general, the limit has to be what in order for this to converge? Ooh, I heard lots of people say things were incorrect. Less than 1, right? Less than 1. for convergence. So this is going to tell us what x has to be. So x has to be, no, not just less than 1. How could the absolute value of x be less than 1? Yeah, between -1 and 1, right? Gives us the absolute value being x being less than 1. So the series converges when x is between -1 and 1. What if x were 1 or -1? What would our limit be? What would that limit be if x were 1 or -1?
Inconclusive.
It'd be 1, right? The limit would be 1. Because if x is 1 or -1, then the limit would be 1, and then we'd have inconclusive. So we have to check that. So we know it converges, we know that series converges when x is between -1 and 1, but if x equals -1 or x equals 1, the jury is out. So we have to do those separately, and all we do is we plug in x equals -1 into the series, and then we analyze it with all the whole toolbox. So the x is gone now, right? So if x is -1, then what do we get? We get -1 to the n over 2n minus 1. And now it's no longer a power series, it's just a series. It's just an infinite series. And we have the ability to do this. Is that convergent or divergent? That's what we're asking. Is that convergent or divergent? -1 to the n over 2n minus 1. What's that?
It'd be convergent
Because
of the alternating series rule, because the series is alternating and the limit of the argument goes to 0. That means that the series will converge.
Right. So yeah, so it's alternating, and then the rest of it, 1 over 2n minus 1, decreases to 0. As n gets bigger, that gets smaller and decreases to 0. So that fits everything we need for the alternating series test, and so it's convergent. So what happens now? So we can include x equals -1 into our set of values x for which it converges. What about x equals 1? So x equals 1, what do we get? When x equals 1, we get 1 over 2n minus 1. And now, for that case, we have to ask, is that convergent or divergent? Why divergent? It's essentially the harmonic series, right? It's essentially the harmonic series.
It's less than. Yeah, it could be.
Okay, what about 1 over 2n? Would be 1/2 of the harmonic series. Divergent or convergent? Certainly divergent, right? And now how does this compare to 1 over 2n? By subtracting 1 from the denominator.
Less than. No, more than.
Greater than, right? So so instead of comparing the harmonic, we can compare to 1/2 the harmonic, right? I should say by comparison to 1 over 2n is what I should say.
Is that sufficient enough to write as work?
It is, but it's 1/2 of the harmonic series. That's not going to help you converge.
So,
See?
but can you say that it diverges, or is it just no conclusion?
No, you can say that it diverges because if you have a divergent series, taking 1/2 of it will never help. Taking 1/10 of it will never help. Taking 1/millionth of it will never help.
So you're saying
So it's not using comparison. You're just using kind of common sense. That says the comparison would be to 1 over 2n because it's greater than 1 over 2n. 1 over 2n minus 1. All the terms are greater because you're making the denominator smaller. So these are all these terms are bigger than these. But I'm not comparing 1 over 2n to the harmonic. I'm arguing that 1/2 of the harmonic series is still going to be divergent. So just because it's less than the harmonic series, all the terms are less than the harmonic series, doesn't mean that there's no conclusion. It means that we're not gonna use the comparison test, and we're gonna say, here we got something that diverges, and now we're just taking half of all those. That's not gonna help it converge. It's still gonna diverge. And then all these terms are gonna be greater than that. Does it help?
Would it be proper to say a constant does not change whether a series diverges or not?
Yes, or converges, right? So if a series converges and you multiply by a constant, it will still converge. If it's divergent and you multiply by a constant, it will still diverge.
Oh, okay, so it's the other way around.
Yeah, so whether it's convergent or divergent, multiplying by a constant will keep the same result. Yeah, John?
Does that mean that any coefficient before n in the denominator could be taken out of the sum, and then you could just say that it is divergent? So that even if it's 1 over 100n, you just throw the 1 over 100.
Mm-hmm. But like I can't factor a 2 out of this, right? It can't have a sum, it would have to simply be a constant times 1 over n, which this is not. Do you see? Okay, are we good? Are we okay? So therefore we know exactly for what x values this converges and diverges now. We knew it was between -1 and 1, and now we're also going to include -1, but we're not going to include 1 because it's divergent at 1. So we say the interval of convergence is -1 less than or equal to x less than 1. Okay, and if we were to graph that, any questions on that? Did you follow that? So the ratio test got us the interval, and then we plug in the endpoints and check those separately. And when we plug in those endpoints, it's no longer a power series. We're just analyzing the series like we've been doing the last 2 weeks. And so we analyze those separately, and then we include or not include the endpoints based on analyzing those series. So if I put that on the number line, it would look like this. So what we see is that this interval of convergence is centered at 0. Okay, it's centered at 0. And if we think of like a circle, what's the radius? If that's the center, then what's the radius of this interval? 1, right? Okay, so we have what's called the radius of convergence, r equals 1. So the radius of convergence is r equals 1. Okay, and so you would say, all right, well, why would we do that if it's just on the number line? Why this circle? Well, I'm currently taking a class called complex analysis, and in complex analysis we do these power series, but we do them instead of the answers being on the number line like this, our answers are actually in the plane. So we have a center, and we truly have a radius of convergence. So like the series will converge for all these points inside this like disk with a radius of convergence, okay? And so that principle then is still like this is a foundational start for that principle coming later when you are in what's called the complex plane. What's that?
Is that imaginary?
Yeah, complex plane. So the x-axis is your real component, and the y-axis is your imaginary component. So numbers are of this form, a plus bi. So your a you graph horizontally, and your b you graph vertically. And so then if you're doing a power series, then you no longer have an interval of convergence, but you have a set like this, a set of values like this with a radius, truly a radius. Okay, so that is analogous to what we're doing here. We just have 2 dimensions, or just 1 dimension for the solution.
Is that true for every point on like the circumference of that disk? Or is that something you find out?
You're talking about what I was talking about?
Oh yeah, like how we included -1 but not 1. Does that apply for like all the points on the circle?
Yeah, so sometimes the boundary is included, sometimes not. Maybe sometimes part of the boundary, part not. So it's a lot more complicated question than just 2 points. Right now you have a whole set of points on the boundary. Yeah. Okay, other questions about this? So sometimes the problem will just ask you for the radius, but other times it will ask you for the interval also. So it could ask you for one or the other or both. Okay, another one. So give this a shot. So the question we always will ask is, here's a power series. For what values of x will the power series converge? Okay, this one's on you. I'm going to keep learning your names here. Where is Natalie? It's Natalie. Farah, Hector, Vincent. Vincent B. You here? Zachary Baker.
Yeah.
Zachary. Go by Zach?
Yes.
Gerardo. So yeah, no. Rusty. Ryan Dykus. Mohammed Habash. Corey. No. Adrian, no. Jacob Hilleran. Carl, I know. Is Carl here today? Trevor, I know. Alec Hutchings. This is Alec Hutchings. Emily Joyner. Ashley, I know up here. Ralph is here. Usually, no Ralph today? He usually sits right there. Logan, I know. Miranda. Brady, I know. John Martin. Elizabeth. Jessica Miller. Ben, I know. Caitlin, I know. Emily Nelson. Andrew, I know. John, I know. Robert Reese. Magali. Rincon, Magali. Ricardo, I know. Junio. Christiana. Andrea. Nikon. Son, last name Son. No, I pronounce his name. Don is here. George. Ten King. Alec Warren is here. Levi. I know Levi. Philip. Chen. No Chen. And Donkey. Currently there are 46.
We lost that the guys never. I think that was just.
He got enrolled, but he never did anything. Okay, what's the conclusion with x's? What happens to the x's? What'd you get for x's in the end? You got x squared. Is that what you got? 1? It's 2, right? Because because it's 2 times n plus 1. You'll have 2n plus 3 on the top and 2n plus 1 on the bottom. So you end up with 2 more x's on the top. And then what about the factorials?
Could we say like 2n plus 2 factorial? And then we take that down by 1.
It's not 2n plus 2 factorial though. It's 2n plus 3. In the denominator?
Yeah.
It's 2n plus 3. What's that? No, because you have 2n plus 1 quantity plus 1. So n is going up by 1. Do you see it? So then you have 2 and then another 1. So it's 3, 2n plus 3. So 2n plus 1 factorial over 2n plus 3 factorial is? That's not what I wanted. Sorry. So you got negative 1 over 2n plus 3 times 2n plus 2 x squared. Now we're going to take the limit. We're going to take the limit as n goes to infinity. What is the limit of this? As n gets really big, what does this whole thing do? 0. 0. What if x is really big? What's the limit as n goes to infinity? 0. 0. Okay? The limit is 0. And when does this converge? When that limit is? Ratio test says the series converges when the limit is less than 1. So we're asking the question, for what values of x is this limit less than 1?
Unless n is part of x.
What's that?
Can you use like
No. Answer, so for what values of x does this limit, is it less than 1? All of them. It doesn't matter what you put in for x. The limit is always 0.
So x is unvariable.
What's that?
X is invariable.
It's a variable, but for any, you're always, you're evaluating the limit as n goes to infinity for any particular value of x.
Okay.
You think of them as
Held constant.
held constant. Yeah, it's held constant, but it can take on any value, but it doesn't change when you're evaluating this limit.
Not within the sequence.
Right.
Set setting.
Right. Okay. Right. So for what values of x is the limit less than 1? All of them. So this power series converges no matter what x is. So the interval is negative infinity to infinity, and the radius is infinity. Does that make sense? So no matter what x is, that limit is 0. Therefore, no matter what x is, that limit's always less than 1. And so no matter what x is, it converges. So we say the interval is all values from negative infinity to infinity, and the radius is infinitely large.
Can you also say that it's similar to conversion?
Oh, for sure. Yeah. Yeah, because that's the ratio test says. The ratio test is a test for absolute convergence. So definitely. Other question, John?
I can't remember why when this when a n plus 1 over a n is equal to 1, why is there no conclusion?
That's a different question.
Yeah, I just can't remember why there would be a conclusion.
Because what's happening is you're multiplying by 1. In the end, you're multiplying by 1 to get the next term. So that may or may not converge. It's not becoming like a geometric series, basically. It's just the terms are becoming all the same. It's not geometric. If it's less than 1, then it's like a geometric series that's converging on a. But if it's just 1, you're just adding like the same thing over and over and over again. Who knows what that is, right?
Is there instances where there is no value for x that will create a convergent series?
Right. Yeah. So if this limit is greater than 1, no matter what x is, then it will be divergent. except maybe if x is 0. So if x is 0, but that's like a trivial case, right? Because you just add a bunch of zeros. Okay, so that web work that has been open, that's due Wednesday. You can work on the power series now. If you have questions, don't hesitate to let us know.